Thank you. All right, so I want to begin by recalling a few definitions that I made last time. So I've written some of them here on this board, or let me push this up to the top. So let's say C is some category that we're going to work in. It could be the category of abelian groups, or the category of vector spaces, or the category of sets. The only thing that's going to be important for the moment is that it has limits and colimits. So if X is a topological space, last time I defined a category that I called C to the X, or denoted C to the X, the category of C-valued local systems on X. And recall what it means to give a local system. It means for every point of X, you give an object of the category C, and anytime you have a path from one point to the other, you're supposed to give an isomorphism between those objects, which you think of as given by parallel transport along that path. And that should satisfy some kind of associative law. All right, so for any category C, you can talk about local systems. And if C has limits and colimits, then it makes sense to talk about two different kinds of push forward for local systems that I denoted last time. Well, let me recall a definition that I gave at the end last time. Well, if F is a map from X to Y, then there's a way of taking local systems on Y and pulling them back to X. So that's what I'm denoting by F upper star. And if C has limits and colimits, then F upper star has a left adjoint, which I'm denoting by F lower shriek, and a right adjoint, which I'm denoting by F lower star. And the problem that I told you I wanted to address last time is to understand situations in which these two adjoints ended up being the same functor. So this is the phenomenon that I'm going to call ambidexterity. A left adjoint and a right adjoint are the same. So I gave a construction last time that should look sort of mysterious. So let me recall this construction. So let's suppose that F is a map from X to Y and that it's a fibration, just for simplicity, and contemplate this diagram here with all of the, we have that fiber product of X cross X over Y with two projections onto X and the diagonal embedding of X into the fiber product. And let's assume that we start with some sort of ambidexterity phenomena for the diagonal map delta. So last time I said, let's assume that delta lower star and delta lower shriek are isomorphic. Well, actually, I didn't need that they were isomorphic. What I needed for this construction was a map from delta lower star to delta lower shriek. So let's say you have such a map alpha. Well, to alpha, you can associate what I'll call the norm map. So that's a natural transformation from F lower shriek to F lower star. And, well, you can read it across the board here. It's given by a composition of some natural isomorphisms, something that involves alpha, and some co-units that come from the adjunctions between F lower shriek, F upper star, and delta lower shriek, delta upper star. So if that still looks opaque, don't worry, because what I'm going to spend most of this lecture doing is unraveling it. Or I'm going to tell you, I'm not going to unravel what I wrote. This is the efficient way to write something that I'm now going to describe more in words. So, but let's ignore the specifics of this definition for a minute. Now I just want to take this construction as a black box and tell you what I mean by ambidexterity. I said it at the end last time, but let me spell it out in a little bit more detail. So, definition. Well, this is a co-inductive definition. So let's say we define a class of maps F from X to Y called ambidextrous maps. And for each ambidextrous map, F well, let's say a norm map, which I'll call norm sub f, that goes from f lower shriek to f lower star. And it'll actually be an isomorphism. OK, so here are the conditions that this definition should satisfy. So first, any homotopy equivalence is ambidextrous. Or any homotopy equivalence f is ambidextrous. And the norm map that's associated to a homotopy equivalence, well, let me say, is the obvious map. So what do I mean by the obvious map? Well, if you have a homotopy equivalence of two spaces, then the pullback functor that takes local systems on y to local systems on x is an equivalence of categories. So an equivalence of categories always has both a left and a right adjoint, and those are both just the inverse equivalents. So for a homotopy equivalence, there's an obvious isomorphism between these two functors. So now so this is where you start. Homotopy equivalences obviously have some kind of ambidexterity phenomena. And for other maps, it's supposed to come from this construction. So let's say it like this. So if f from x to y is a fibration, and you can always convert any map into a fibration by replacing your spaces by homotopy equivalent ones, and delta is ambidextrous, then define the norm map, norm f, from f lower shriek to f lower star. Well, let's say use it taking alpha to be the inverse of the norm map that you constructed for delta. So up here I said the input to run this construction is you need a natural transformation from delta lower star to delta lower shriek. So if you've got an isomorphism in particular, that's a natural transformation. So take the norm map that you've constructed for the diagonal already. If it's invertible, you can take its inverse, and that constructs a norm map for f. So then we'll say that f is ambidextrous if norm f is an isomorphism. So now what do I mean by this definition? What I want is to take the class of ambidextrous maps to be the smallest class that satisfies these conditions. Namely, a map is ambidextrous. The only way that a map is ambidextrous is if you run this construction finitely many times and eventually you get to a homotopy equivalence. So I'm going to spell out how that works for you in just a minute. But first I want to make two comments. So I want to give you a way of thinking about what this construction does. So, well, my first comment is for almost all purposes, it's sufficient to assume y to be a point. That is, all of these constructions are really Fiberwise constructions. If you think about what f lower shriek and f lower star are doing, if you take a local system on x, you make a local system on y. And if you want to know what that local system looks like at a point of y, you only have to think about the fiber over that point and what your local system on x looks like along that fiber. So if you want to construct an isomorphism between these two push forwards, well, the real case you want to understand is the case where y is a point. But the general case is just saying that you can handle the case where y is a point, but you can do it uniformly. You can do it in a way that makes sense in families. And that's important for giving this definition, but maybe it's important not to think about it when you're trying to understand the definition. So let's take y to be a point. And let me just make a remark that, let me make another definition. So to emphasize the case where y is a point, we will say a space X is ambidextrous if the projection map from X to a point is ambidextrous. So then, in that case, for any local system, script L on X, we get an isomorphism. If you look at what this norm map is doing for the projection from X to a point, this is giving you an isomorphism between what I called earlier the homology of X with coefficients in L to the cohomology of X with coefficients in L. So how does this condition of a space being ambidextrous relate to the condition that a map of spaces is ambidextrous? Well, if you have a map of spaces which is ambidextrous, and let's say it's a fibration, then each fiber will be an ambidextrous space. And the converse is almost true. Namely, if you have a map whose fibers are all ambidextrous and there's some upper bound on their homotopy groups, then the whole map is ambidextrous by that definition. So let's focus on the case of just a single space mapping to a point. So now the next thing I want to do is think a little bit about what it means to have a natural transformation, let's say going in this direction up here, from delta lower star to delta lower shriek. And let's treat the case of a point. So let's say that F is a map from X to a point, and alpha is a natural transformation from F lower star to F lower shriek. So what does alpha buy you? Well, having such a natural transformation, what it buys you is a sort of integration procedure. So I want to just think about what alpha will tell you when you put in a trivial local system. So let's suppose C and D are objects of the category C. And suppose we have a map a map from X to the collection of morphisms from C to D. So we've got some family of morphisms from C to D which is parametrized by the space X. So here's what I want to do. So let's take F upper star of C and F upper star of D. So here C and D are objects of script C, so I can think about them as local systems on a point. And I can take those local systems and pull them back to X. So here these are just the constant local systems with value C and D. They assign C and D respectively to any point, and they assign the identity isomorphism to any path. So these are some boring local systems, but let's call this map something. Let's call this rho. But rho is a possibly interesting map between them. If you have, for every point of X, a map from C to D, and I should have emphasized that this was continuous, meaning that this, in the setting we're working now, meaning this is a locally constant function on X with values in homs from C to D. Well, that determines a map from the constant local system with value C to the constant local system with value D. So now we could take this map and push it forward. So we could take F lower star, F upper star C. That maps by F lower star of rho to F lower star, F upper star D. And now let's use alpha here to get to F lower shriek, F upper star D. So this here is the cohomology of the trivial local system with value c. And just by definition of what f lower star means, there's a canonical map from C into here, which is like the diagonal map. And by the same token, there's a canonical map from here into D, which you can think of as some kind of codiagonal. And if you look at this composition, it's some kind of map from C to D. And it's a map that you've obtained starting from a family of maps from C to D, which is parametrized by x. So what I would like to give this map a name. I would like to call this the integral over x of rho. So if we have a family of maps from C to D parametrized by x, and we also have a natural transformation alpha like this, then it gives us some way of taking there's some integration procedure which takes all those maps and combines them into one. And this depends on alpha, so I don't know. Maybe we could emphasize that by writing integral of rho d alpha or something like that. But all right. So now let me tell you what this construction is in more concrete terms. So there's now so let's suppose now that f is a map from x to a point. That's always going to be a fibration. And let's let delta be a map from x, be the diagonal map from x to x cross x. And now suppose that we're in the situation of this board up here. So we're giving ourselves a natural transformation from delta lower star to delta lower shriek. So now how can you, so I told you this lets you construct a natural map from f lower shriek to f lower star, and now I just want to write a formula for what it is in terms of the notation I've introduced over here. So let's say L is a local system on X. So now, what is f lower shriek of L? Well, that's the thing I called the homology of X with coefficients in L. And remember what it means. This just means the direct limit of L sub x taken over all points x in X. And now, the norm is supposed to give me some map to f lower star of L. And this is what I called the cohomology of X with coefficients in L. And remember the formula for that. That's just the inverse limit over all points y in X of L sub y. So now what does it mean to give a map from the left-hand side to the right-hand side? We're mapping from a direct limit to an inverse limit. Well, what it means is that for every x and every y, you have to give a map from L sub x to L sub y. So let me say that this map here is given by something you might think of as a matrix. It's given by, well, why don't I call it? It has matrix coefficients, which I'll call norm f of L sub x comma y. And each of these is just a map from L sub x to L sub y. So here's the formula for those matrix coefficients. To take the norm of f of x comma y, or norm f of L of x comma y, this is given by that integration procedure on the other board. So what we're supposed to do is integrate over all paths p from x to y of, well, to every path from x to y, L is a local system. Every path gives us an isomorphism of L sub x with L sub y. So let's take those isomorphisms. So up here I called them L sub p. So don't be confused. This is not an object of C. It's a morphism in C. And we integrate this over the space of paths. And I'll write d alpha to emphasize that we're using the natural transformation alpha, or we're using what alpha tells us to do. So that's what this construction is. Given alpha it gives you some sort of integration procedure, and that gives you the matrix coefficients for this natural transformation. OK, so now I've hopefully equipped you with a way of thinking about what's going on, and now I would like to spell it out in some examples. And the examples will start out very easy, and then they'll get a little more interesting. OK, so I want to start with the easiest non-trivial example. So I'm always going to take y to be a point in this situation. So the complications are going to come from x. And if x is also a point, nothing interesting is going on, because this map is a homotopy equivalence. So the next simplest space I can think of is where x is the empty set. So let's start there. So let's call this example 0. Let's take x to be empty. So now, what happens when x is the empty set? And you draw this diagram up here. So we have the empty set mapping to a point, the empty set. And now if we form this fiber product, that's the empty set. And the diagonal map from x into the empty set is an isomorphism. So that's good. Because remember, to start this construction, we need to already have some kind of data, some kind of natural transformation, alpha, which is associated to the diagonal. So in this case, there's nothing to do. OK, so let me call this map F. This is the map from an empty set to one point. So F determines two functors, F lower shriek and F lower star. And those functors go from the category of local systems on the empty set to the category of local systems on a point. So now what is the category of local systems on the empty set? Well, to specify a local system on the empty set, you don't have to do anything. You don't have to specify any data on that right-hand board. That means this is a category with a unique object, which I will also denote by a point. What about a local system on a one-point set? Well, this is just the category C again. So what are these functors? Well, to specify a functor from the one-point category into C, you just have to specify an object of C. So why don't I, if it's not too confusing, just say F lower shriek and F lower star, you can think are objects of C. And which objects are they? Well, F lower shriek is the initial object. And F lower star, this is the final object. And now what is the norm map? So this is supposed to be a natural transformation from F lower shriek to F lower star. Well, there's only one choice for what it can be, right? It's a map from the initial object to the final object of your category, and there's only one of those. There's two different reasons why there's only one of those. So that's what this constructs in this example of the empty set. So now what does it mean for the empty set to be ambidextrous? That means that this map should be an isomorphism. So what's the upshot of this discussion? So the upshot is that the empty set is ambidextrous. That's an interesting condition on C. This is equivalent to saying that the category C is pointed, i.e., C has a zero object, meaning an object which is simultaneously initial and final. So this is true for some categories and false for other categories. So for example, if C is the category of sets, the empty set is not ambidextrous. But if C is the category of groups, then the empty set is ambidextrous, because in the category of groups, the trivial group is both an initial object and a final object. So things like groups, abelian groups, vector spaces, those categories are OK. The category of sets is not. All right, so now I erase this discussion of when having an ambidextrous space, well, it in particular gives you the inverse of the norm map, which I told you gives you some kind of integration procedure. So what is the integration procedure in this case? So the integration rule Well, what I'm saying is, if you have a map from the empty set into Homs in C from X from C to D, then we get a new Hom, which we'll call, so let's call this map rho again. We can integrate rho over the empty set to get another map from Homs from C to D. So let me call this integration over the empty set, let me call that the zero map in Homs from C to D. And what is the zero map? Well, if you take any two objects in your category C and D, let 0 denote the zero object, the object which is both initial and final. There's a unique map from C to 0, and there's a unique map from 0 to D. And if you compose them, you get a map from C to D, which you might call the zero map. And that's what this integration procedure gives you. If you integrate over the empty set, you get 0. So that's not very interesting, but keep it in mind for what's going to happen next. So I want to keep that. I want to keep that. Oh, I don't think I want to keep this. So I wrote this at the beginning just because I wrote this formula last time. This formula is just unwinding the explicit description that I gave you on this board here. If you try and take this and make it rigorous, or write it down with your T's crossed and so forth, then you'll write this composition. But never mind. Let's move on. So we've done the case where X is the empty set. And now we're prepared to think, let's say we have a map from X to a point, and we take the fiber product X cross X, and we consider the diagonal embedding of X into there. So what are we now prepared to think about? Suppose we fix a pointed category C, so the empty set is ambidextrous. Then a map is going to be ambidextrous as long as its fibers are either contractible or empty. So delta will be ambidextrous as long as, well, for example, whenever X is discrete. When X is discrete, all of the fibers of delta are either empty or contractible. So let's assume that X is discrete. So now how can you think about a local system on X? Well, that means you have to supply an object of your category to every point of X. And this other data, this thing having to do with paths and compatibilities for two simplices, you can ignore all of that. There are no interesting paths here. So you just need to specify a collection of objects of C indexed by X. So let me write that as C to the X. Well, I don't know. C to the X equals C to the X. It's a product of copies of C indexed by X. So now there are two natural transformations, F lower shriek and F lower star, that go from C to the X into C. And what are they? So F lower shriek of a local system L, what this does, or maybe I'll write F lower star first. So F lower star of L, this is just the product over all X in X of what your local system looks like at that point. And F lower shriek of L, it's the dual thing. It's just the coproduct over all X in X of L sub X. And actually, to make this look like the previous discussion, why don't I call this the product over all Y in X, L sub Y. So now, what does our discussion tell us? Well, if the empty set is ambidextrous, we get a norm map, which goes from here to here. And there's a formula for it. So what does that formula say? Well, a map from this coproduct to this product, it's given by an X by X matrix of maps. And what maps are we supposed to take? Well, along the diagonal, you're supposed to take the identity map. And off the diagonal, you're supposed to apply this integration procedure, which I told you over here, it just gives you the zero map. So this you could think of as given by the identity matrix with 1s along the diagonal and 0s off the diagonal. So what does it mean for x to be ambidextrous? So x is ambidextrous if and only if, well, why don't I say it like this, the identity x by x matrix is an isomorphism. It gives you an isomorphism from a coproduct of objects indexed by x to the product of objects indexed by x. So this happens sometimes and fails other times. So for example, if we're talking about the category of groups, the empty set is ambidextrous because the initial object and the final object are the same. But for example, a 2-point set is not ambidextrous because in the category of groups, there's a natural map from the coproduct of two groups. That's the free amalgamated product of two groups. Or not amalgamated. The free product of two groups maps to the Cartesian product of two groups. But that map is usually not an isomorphism. If you took two copies of the integers, then you're talking on the left-hand side about a free group on two generators, and on the right-hand side, the free abelian group on two generators. So the category of groups is bad for this discussion. On the other hand, if you were working in the category of abelian groups, you would be OK. You would be OK if x is finite. But if x is infinite, you're also out of luck. So if x is infinite, the left-hand side, if you have an infinite collection of abelian groups, you can take their direct sum and you can take their direct product. And the direct sum embeds into the direct product via this map. But that map is usually not an isomorphism. OK, so now what do I want to erase? How about this? So I should also mention you get an integration procedure. So let's assume C has the property that finite sets are ambidextrous. So what's that condition? Well, it's the condition that you have a zero object and that finite direct sums and finite direct products are the same. So then C, this integration procedure discussion tells you, well, let me call this C is semi-additive. What happens? Well, if you look at Homs in C between any two objects C and D, this has the structure of a commutative monoid. So every finite set is ambidextrous. And that integration discussion before tells you what that means is anytime you have a finite set, a family of morphisms from C to D parametrized by a finite set, then you can integrate the family. So in this case, that just means adding the morphisms. So what is that construction explicitly? You take C and you embed that into a product of copies of C indexed by X, and then you apply all of your different morphisms to get into a product of copies of D indexed by X. And then this product is the same as the coproduct, so you can map it back into D. So this is the usual way that you add morphisms if we're in the category of abelian groups. The sum of two maps of abelian groups can be obtained by first embedding diagonally, then implying the morphism F comma G, and then projecting back into the target group. So more generally, whenever you have a category where finite sets are ambidextrous, you get some kind of an addition law on the Homs sets. And that will always make them into a commutative monoid, although in this context, there's nothing that requires that there be additive inverses. OK, so let's suppose that we're in this setting. All finite sets are ambidextrous. That lets us build a new norm map. So what kind of norm maps can we now consider? Well, let's take y to be a point as before. And now what we want to think about let's think about this diagram here. X maps to a point. Here we have x cross x. And we have x embedded diagonally in here. And what we want to think about is when this is an ambidextrous map. So we've said all finite sets are ambidextrous. So that map will be ambidextrous if its homotopy, it's equivalent to a map which is a covering space with finite fibers. So let's call this map delta. Let's call this map F. So note, delta is ambidextrous. So for example, if x is equal to bg, where g is a finite group. So now what is a local system on bg? So this category of local systems on bg, you can think about this as the category of objects of C with an action of G.
Why was delta ambidextrous in that case?
Well, so the diagonal map from BG into BG cross BG is equivalent to a map whose fibers are look like G. So if you wanted to build, if you look at the, say, E of G cross G, you can mod out by the diagonal G, and you can mod out by G cross G. And this is a model for BG cross BG. This is a model for BG. This whole picture is a model for the diagonal map. And this way of describing it makes it clear that this map has finite fibers. And the size of the fibers is the cardinality of G. So when we talk about local systems on BG, we're talking about objects with an action of G. And now what are these constructions? So what is F lower? So let me now not denote them by L. Let me denote them by V. I want to think of them as representations of G. So what are these two functors? F lower shriek of V. Well, this is what you might call V lower G. This is the co-invariant construction. If we were in the category of abelian groups, this is given by the construction that I described last time, where you take V and you mod out by everything of the form gx minus x. And F lower star V, this is given by G invariants. If we're in the category of abelian groups, this is just the subgroup of V consisting of elements that are fixed by the action of G. And now what we're constructing here is some kind of norm map from V sub lower G to V upper G. And if you look at what this description is telling you to do, this description right here, you see that that's the same as the norm map that I described in my previous lecture. That's the usual map where you take an element of V and you average it over the group to produce another element of V, which factors through covariance as factors through passage to covariance and lands in the invariants. So this is a reconstruction of the classical norm map. Okay, so why did it take me a lecture and a half to reconstruct something that I just wrote down for you in the middle of the last lecture? What is the point of all of this discussion? We got this classical norm map. We could have just written a formula for it anyway. Well, the point is that as soon as you've got a norm map, you can ask if it's an isomorphism. And if it's an isomorphism, that lets you go on to construct something new. So let's now suppose that we're in a setting where this norm map is always an isomorphism. So, well, what's the upshot? So the space BG is ambidextrous if for any representation of G, this norm map is an isomorphism. So that's not always true. If we're in the category of abelian groups, that's usually not true. But if we're in the category of complex vector spaces, it is true because we're allowed to divide by the order of G. So some categories will have BG be ambidextrous, like if we could divide by the order of G, and some will not. But let's assume that BG is ambidextrous. So are there any questions about the definition that I'm erasing now? So
yes.
Yes.
You defined the first condition was that homotopy equivalence is ambidextrous, but is there a reason why you didn't say that just prove up why F was equivalence of categories?
Well, you could try starting this construction if you had a map, where the pullback was an equivalence, and you may or may not produce something consistent. I don't know.
Okay.
I think you usually won't for reasons that'll become clear in a little bit. But OK, so what am I doing now? Right, so suppose BG is ambidextrous. So G is here as a finite group. And let's suppose that G is abelian. Well, in this case, I can go on and consider, let's take X to be the space KG2, Eilenberg-MacLane space. So this space is characterized by the following properties, that the homotopy groups of X should be G if I is equal to 2 and 0 otherwise. So there is a space, say a CW complex with this property, and moreover, it's characterized up to homotopy equivalence by this property. So let's take that to be our X. Let's let F be the projection map from X to a point, and let's contemplate this diagram, X cross X, and consider the diagonal map from X into here. Now in this case, the homotopy fibers of this map delta, and once you convert this map into a fibration, its fibers are going to look like copies of BG. So if BG is ambidextrous, this implies that delta is ambidextrous. So that lets you construct something which now, well, is maybe not familiar. Well, it is familiar, but you'll see in a second. As you'll see in a second. So if L is a local system on BG, on X, which is a KG2, then what I'm saying is we get a canonical map, H lower 0, from the homology of L to the cohomology of L, which is the norm map that's associated to this F. So this is maybe not so familiar. What is it given by? Well, you're supposed to sort of produce this map by some sort of procedure where you integrate over the path spaces in X. So you're integrating over spaces that are like BG. So this map is not very interesting for the following reason. L cannot possibly be interesting. Because if you go back to the definition over here, remember that a local system on a space only sees the fundamental groupoid of a space. It's a representation of the fundamental groupoid. So if you have a simply connected space, every local system is trivial. The category of local systems is equivalent to the original category C, and these functors of homology and cohomology are the same as the functors that you would get, say, by evaluating at a point. So these constructions are not interesting. Nevertheless, this map is slightly interesting, because this map is not the identity map. So this map is given by multiplication, well, by 1 over the order of G. Say if we're in the setting of complex vector spaces. This is what you get when you take the identity map and in some sense integrate it over BG. So this is, to answer Andre's question from the first lecture, maybe this is a more convincing explanation of why you put these factors in. These factors come out of this general construction of these norm maps. So, okay, it's slightly interesting because this was not the identity map, but not terribly interesting. So I want to tell you a story about these norm maps going up and considering more and more complicated spaces X. But that's not going to be terribly interesting if we consider local systems with values in a category. So now I need to go, and fortunately Chris has been giving lectures all week about higher category theory. So now I'm going to replace X by what in Chris's lectures would have been called an infinity 1 category. So as Chris mentioned, there's all kinds of different definitions you can give of what this means. I don't want to dwell on any of them, but the way that you can think about an infinity 1 category is it's got a collection of objects, and for any two objects there's a space of maps between them. An infinity 0 category of maps between them, which I'm going to think of as a topological space. So now if X is a topological space, it again makes sense to talk about C-valued local systems on X. The definition is slightly different. Well, we should supply an object for every point, an isomorphism for every path. And now if we have a 2-simplex, we're not supposed to say that these two isomorphisms are the same. But what we should really say is that we supply a homotopy between every 2-simplex is supposed to give us a homotopy between these two isomorphisms. So, or in other words, if we're in an infinity 1 category, we should supply a 2-morphism which is invertible. And furthermore, we have to write ... here, meaning we supply data like this for every simplex of higher dimensions, for all simplices of all higher dimensions. And another way you can think about this, in this context, this notation of c to the x really makes sense because, as Chris mentioned, a space is something that you can think of as a special case of a higher category. And this is just, if you think of x as a higher category, this is really some kind of category of functors from x into c. So let me just mention some examples that you might want to keep in mind. So I've already mentioned a bunch of examples of ordinary categories, so let's get some examples of things that aren't ordinary categories. So an example would be, C could be the topological spaces. So topological spaces can be organized into one of these infinity 1 categories because you have not only a notion of a continuous map between topological spaces, but also a notion of homotopy between continuous map, which will be your 2 morphisms. And you can consider homotopies between homotopies and so on and so forth. So that's a good example to keep in mind. A better example for purposes that I'm going to talk about, we could take C to be chain complexes. Let's say of R modules, where R is some ring. So the category of R module, if you have in the setting of chain complexes, there's again an infinity category that you can talk about, where your objects are chain complexes, your morphisms are chain maps, and your 2 morphisms are homotopies between chain maps. And a fancier version of this, which I'm going to come back to in the next lecture, is you could take C to be something like the infinity category of spectra, which is well, it's a fancier version of chain complexes where you take R to be a ring spectrum rather than an ordinary ring. But these are the kinds of infinity categories that I want to consider now. And in these settings, in this setting, it's no longer true that a simply connected space has no interesting local systems. There can be lots of interesting local systems on a simply connected space. You don't see the interesting part when you think about the data that you're associating to 0 simplices and 1 simplices, but it gets interesting when you think about 2 simplices and above. So everything that I've said so far makes sense in this more general context of infinity 1 categories. You can talk if C is an infinity 1 category, you can talk about local systems with values in C via this definition. You can talk about pulling them back and pushing them forward. Well, push forwards require the assumption that C has limits and colimits, which makes sense in this setting. And you can start trying to construct these norm maps. You can give the same construction that I described here. And it has the potential to be more interesting once you hit spaces like KG2. So let's take an example. So let's let K be a field. And let's take C to be chain complexes of K vector spaces. And let's ask, which spaces are ambidextrous if this is our category C? So first, the empty set is ambidextrous. That's the analysis that we went through just a little while ago. That's the condition that there be a zero object. There's an object which is both initial and final. And that's just the chain complex which is 0 in every degree. So now we can proceed to ask if finite sets are ambidextrous. Oh, sorry. As an aside, well, why don't I... Just to emphasize, so this formalism might not be familiar to you, but I claim that these constructions are familiar to you in at least one example. So there's an object of C, which I'll just denote by K. So that, I mean, take the field K and put it as a chain complex concentrated in degree 0. So now let X be a space, and let L be the constant local system with value K. So it assigns to every point just a chain complex concentrated in degree 0 with value K. There's nothing interesting about this local system. So now, what do you get? So let's let F be the projection map from X to a point. And let's ask what happens when you apply these two constructions to this local system L. So you're supposed to produce chain complexes of K vector spaces. And they're really only defined up to isomorphism, which in this context really means quasi-isomorphism. But what do you get? Well, you get familiar things. So in this, if you were to take F lower shriek, what you get is singular chains on X with values in the field K. If you were to take F lower star of L, you would get singular cochains on X with values in L. So these are chain complexes which compute the homology and cohomology of X respectively. So when we ask about ambidexterity in this context, we're asking, in particular, if the homology and cohomology of X should look the same. And now we're not just talking about degree 0, we're talking potentially about all degrees. So for the empty set, homology and cohomology look the same. Finite sets are also ambidextrous. Remember what that means? That means that direct sums and direct products, finite direct sums and finite direct products, should be the same in this category, and they are. But it gets more interesting when we get to BG. So let G be a finite group. We could ask the question, is BG ambidextrous? And the answer depends on K. So what is this question? Well, now we're talking about chain complexes with an action of G. And if you have a chain complex with an action of G, you can talk about the homology and cohomology of G with coefficients in that chain complex. And there's a canonical map from the homology to the cohomology given by this norm construction. So the failure of that norm map to be an isomorphism is measured by what's called Tate cohomology. So when we ask whether or not this is true, what we're asking about is if take cohomology is always 0. So this happens sometimes. It happens exactly when each of the primes dividing the order of G is invertible in K. Or in other words, if and only if the order of G is not divisible by the characteristic of K. So if we're in characteristic 0, all finite groups are OK. But if we're in characteristic P, well, all P groups are bad, for example. So let's just say sometimes. Now, if BG is not ambidextrous, we don't get to go on. We don't get to construct this norm map for X being KG2. So let's put ourselves in a situation where we can construct a norm map. Let's, for example, take K to be a field of characteristic 0. So sometimes, e.g., like if we took K to be the field of complex numbers. OK, so let's take K to be the complex numbers. Then if we have any local system on KG2 with coefficients in this category of chain complexes, or this infinity category of chain complexes, we get a norm map. Potentially it's interesting. But actually it isn't. Because it turns out that in this context, we've again put ourselves in a situation where all local systems are automatically trivial. This time it's not because our category level isn't high enough. There's a potential to have interesting local systems on simply connected spaces. But the interesting local systems are going to involve some kind of interplay between the homotopy groups of X and the field we're working over, the field of complex numbers. And if we're in a particular situation where our homotopy groups are all finite, then the category of local systems is not going to detect that they're there. So, well, bad news. This is automatically trivial. Well, the good news is that KG2 is ambidextrous. It's not that interesting because, again, this local system is trivial. This map is just multiplication by 1 over the order of G. And that's sort of obviously an isomorphism. So then you could say, all right, that KG2 is ambidextrous. That lets me make a norm map for KG3. But that's not interesting because all local systems on KG3 are trivial. The norm map is an isomorphism. It's multiplication now by the order of G. And you can go on and on. You get lots of ambidextrous spaces, lots of norm maps that are not really doing anything terribly interesting. OK, so you would see something interesting. You would see lots of interesting local systems if you took K to be a field of characteristic P. But the downside of that is ambidexterity stops before you can construct any interesting norm maps. The only map that comes out of this procedure is one that you can write down explicitly, and I did it in the last lecture, just averaging over the order over the group. So wouldn't it be nice if we could put ourselves in some kind of a situation where we had lots of interesting local systems, and nevertheless these norm maps were always isomorphisms, so that we were in a situation where homology and cohomology are the same, and it isn't because they're both trivial. It's because of some mysterious duality phenomenon. So that would be nice, and I will tell you about that in the next lecture.
Questions?
Is there a target category in which odd-dimensional manifolds are going to be ambidextrous?
Well, for any manifolds, you want to take a
Question.
Oh, OK. The question is there a category in which odd-dimensional manifolds are ambidextrous? So by the definition that I gave, a space can only be ambidextrous if it has only finitely many homotopy groups. So the only manifold that satisfies that condition is S1. And I think S1 will usually fail to be ambidextrous.
But I'm thinking, like you want an isomorphism between homology and cohomology.
Yes, it's some kind of Poincare duality phenomenon. And manifolds have such a thing, but it doesn't arise via this construction. In the case of manifolds, there's some kind of shift by the dimension of the manifold. So one way of saying this is to say that a space is ambidextrous is to say that it satisfies some kind of Poincare duality which makes it behave like a manifold of dimension 0. So a manifold of dimension n has a similar duality phenomenon for a different reason. It behaves like a manifold of dimension n. So these are not the same phenomena, but you can mix them together. So for example, if you're in a situation where finite groups are ambidextrous, then you have Poincare duality for orbifolds.
Other questions? All right, well, that thing's checked up again.
Thank you.